All right, we're just going to go through and do a bunch of examples now. And these are all going to be constant coefficient, linear, higher order, homogeneous equations. And we're going to focus on the case where we have two distinct roots. We'll see an example where it breaks down, but we won't actually solve it, leaving that for another day. So first example is y double prime minus 5y plus 6y is 0. Now, one thing we didn't say in the previous video is that it's ambiguous what the independent variable is. I'm just going to assume that this is a function of t. If you decide to use a different function like in the book, that's fine. Or I should say different independent variable, that's fine. Just be consistent and go with it. From the original equation, there's not enough to tell us. So we're going to assume that it looks like r times e to the nt. I'm going to take derivatives. First derivative is r e to the nt times n. Second derivative is r e to the nt times n squared. Plug it back into the original equation. Second derivative is r e to the nt times n squared minus 5 times the first derivative, which is r e to the nt times n, plus 6 times the function, which is r e to the nt, set it equal to 0. So what I just did is I plugged my solutions back into the original equation. There's an r e to the nt in every term, so I can factor that out, leaving me with an n squared minus 5n plus 6 is 0. I don't want r to be 0, because then I'd have 0 for my solution. So that means that n squared minus 5n plus 6 is 0. Now, when you get to this point, you can either factor it, or if you cannot immediately see how to factor it, that's fine. Just go straight to the quadratic equation. Don't mess around with it. So you should be able to see in this case, this is going to be what? N minus 2, n minus 3. So n is 2 or 3. If you did not see that, you could just go with quadratic equation. Minus a minus 5 is plus 5. Plus or minus b squared is minus 5 squared. Minus 4 times 1 times 6, because there's a factor of 1 there. All over 2 times a. So cleaning this up, I'm going to get 5 plus or minus. 5 squared is 25. 4 times 6 is 24. So this is 5 plus or minus square root of 1 over 2. For the plus, I'm going to have 5 plus 1 is 6 divided by 2 is 3. For the minus, 5 minus 1 is 4 over 2 is 2. So I get the same thing either way. So that means my solution is y of t is r1 e to the 3t plus r2 e to the 2t. Now, it's just as important for you to be able to look at these numbers and understand what this means about the general behavior. This term here grows exponentially like e to the 2t. This term also grows exponentially like e to the 3t. The question is which one grows faster? Because 2 is smaller than 3, this will not grow as fast as e to the 3t. E to the 3t grows much faster than e to the 2t. After a short amount of time, e to the 3t will be much bigger than e to the 2t. And so the whole solution grows exponentially like e to the 3t. So given a solution, or given a differential equation, you should be able to find the solution, but you should also be able to express the general behavior. So we're going to see situations where we'll have oscillations, and the amplitude of the oscillations are going to grow or decay, and you should be able to discuss all of those things. Okay, let's do another example. So x double prime minus 2x prime minus 8x equals 0. So it's constant coefficient. We have 1, minus 2, minus 8. It's second order, so we should have two solutions, and it's homogeneous because there's a 0 there. That means I can take a guess that x of t equals re to the nt. If the guess doesn't work, that's fine. We'll try something else. If it does work, we'll go with it. That's fine. I'm going to take derivatives. So I get re to the nt times n for the first derivative. For the second derivative, get re to the nt times n squared. Plug those back into the original equation. So x double prime is re to the nt n squared minus 2 times x prime. So I get minus 2r e to the nt n minus 8x. So that's minus 8. R to the nt is 0. Every term has an re to the nt, so I can factor that out, leaving behind n squared minus 2n minus 8 is 0. I don't want r to be 0. The exponential can't be 0. So I get n squared minus 2n minus 8 is 0. And I'm just going to recognize that I can factor this. And this is going to be what? N plus 2 times n minus 4. So n1 is minus 2, n2 is 4. So x of t is going to be r1 e to the minus 2t plus r2 e to the 4t. How does this behave? Well, this thing decays. This thing grows. So the whole thing is going to grow like e to the 4t. The dominant term is e to the 4t, right? After a short amount of time, this gets close to 0, and this thing keeps growing. So this is the biggest term that matters. All right, let's do another example. So in this example, we have x double prime plus 4x is 0. Constant coefficient, 1, 4, second order, so it's higher order. And it's homogeneous because there's a 0 there. So I'm going to assume x equals re to the nt. So I'm going to take this first derivative, get re to the nt times n. Take the second derivative, get re to the nt times n squared. Plug it back in. X double prime is re to the nt n squared plus 4x. X is re to the nt. I'm getting these from these three equations. That has to equal 0 in the original equation. I can factor out an re to the nt. Get n squared plus 4 is 0. So again, I don't want r to be 0, so that means n squared plus 4 is 0. I can't factor that. So minus b, b is 0, so that's 0 plus or minus. 0 squared minus 4, a is 1, c is 4. 2 times 1 for the denominator. So I'm going to get minus 16 over 2 plus or minus. And that is plus or minus 4i over 2. That's going to be plus or minus 2i. So good news is I have two solutions. So you would think x of t is going to be r1 e to the 2it plus r2 e to the minus 2it. This is correct and this works, but it's very difficult to understand this and try to talk about what's the behavior. We're going to come back to that. And we're going to look at this separately, but it's important for now to recognize it's not that big a deal because e to the 2t times I, we can use Euler's formula, is going to be cosine 2t plus I sine of 2t. We are going to use that later and come back to that. But for now, recognize it's not a big deal. We can deal with it. It's just that we have to take a little extra step and a little extra time. All right. So let's look at another example. So in this example, we're going to use x double prime plus 10x prime plus 24x equals 0. But we're going to include a little bit of extra information. X of 0 is 2 and x prime of 0 is 1. so far what we've done is we've found a general solution. And basically we didn't solve for the constants. Because we're given two pieces of information, we're now going to find the particular solution. Okay, so the way we're going to do this is we're going to find the general solution first, then we're going to use the initial conditions to figure out the values of the constants. Okay, so when you see a problem, you need to recognize what kind of equation it is, but you also have to recognize, are you finding a general solution or are you finding the particular solution? In either case, the first step is to find a general solution, but here we're going to go an extra step to find the particular solution. So for the general solution, this is second order, so it's higher order, it's constant coefficient, and it's homogeneous. So I'm going to assume the solution looks like r times e to the nt. I'm going to plug that into the original equation, so I need to find the derivatives. So the first derivative is r e to the nt times n, second derivative is r e to the nt times n squared. Plug back into the original equation, so I get x double prime is r e to the nt n squared, plus 10x prime is 10 r e to the nt times n, plus 24x is 24 e to the nt equals 0. So I've plugged into that. I've got an r e to the nt, r e to the nt, r e to the nt in every term, so I can factor that out. I'm left with a 10 squared term there, 10n term there, and a 24 there. I don't want r to be 0, so I have n squared plus 10n plus 24 is 0. Okay, again, I can factor this. I can recognize that this is n plus 4 times n plus 6 is 0. If you did not immediately see that, no big deal. Just use quadratic equation. So I get that n is minus 4 or n is minus 6. I'm going to call that n1 and n2. All right, because either this term is 0 or this term is 0. So my general solution, let me write that more neatly. My general solution is r1 e to the minus 4 1t plus r2 e to the minus 6 2. That should be e to the minus 4t, sorry. Got carried away. And you should notice, this thing decays, and this decays, but because n1 is bigger, that's going to be the dominant term. So for the general solution, you can look at this and say this thing is going to decay like e to the minus 4t. Okay? And after a short amount of time, e to the minus 6t is going to be much closer to 0. It's going to be really close to 0, and this is going to be the term that's left. However, in this case, I have information I can figure out what R1 and R2 is. So what do we have? Oops. We have x of t is R1 e to the minus 4t plus R2 e to the minus 6t. We are given that when t equals 0, x is 0, and when t is 0, x prime is 1. I'm going to basically plug in t equals 0 to this equation, set it equal to 2. I'm going to take the derivative, plug in t equals 0 and set it equal to 1. So I'm going to need to take the derivative. So the derivative of e to the minus 4t is e to the minus 4t times minus 4. Derivative of e to the minus 6t is e to the minus 6t times minus 6. So now, for this equation, I know it's equal to 2. If I plug in t equals 0 into this, I'm going to get r1 e to the 0 plus r2 e to the 0. So this is minus 4, 0, minus 6, 0. So 2 is equal to r1 plus r2. Now using this equation, I know that when I plug in t equals 0 to x prime, it's got to be equal to 1. So this is going to be r1. So t is 0, that's going to be 0 times minus 4. When t is 0, minus 6t is 0, so this is e to the 0 times minus 6. So I get 1 equals minus 4 r1 minus 6 r2. Those are my two equations, two unknowns. So I've got r1 plus r2 is 2, minus 4 r1 minus 6 r2 is 1. Let's do this. So there's a lot of ways to do this. You could solve for 1 and solve for r1 in this equation and plug it in and solve it. I'm going to do it a little differently. We're going to see later on why this is nicer. But I'm going to take the first equation and multiply everything by 4. So I get 4r1 plus 4r2 equals 8. I'm going to leave the second equation alone. Now when I add them together, 4r1 minus 4r1 is 0. 4r2 minus 6r2 is minus 2r2. 8 plus 1 is 9. So I get r2 is minus 9 halves. Now using this equation, r1 plus r2 is 2. I know that r2 is minus 9 halves. So r1 is going to be 2 plus 9 halves. I'm going to write 2 as 4 halves. So r1 is 13 halves. What does this mean? This means now that my solution, x of t, is r1 times e to the minus 4t plus r2, which is minus 9 halves, e to the minus 6t. And that's my solution there. Again, notice that e to the minus 4t is the dominant term. The whole thing is going to decay to 0, but it's going to decay to 0 like e to the minus 4t. Okay. I am going to do two examples here with higher order equations, just so you see how things don't really change. So for the next example, I have x triple prime plus 2x double prime minus x prime minus 2x is 0. Constant coefficient, got 1, 2, minus 1, minus 2. It's linear, not multiplying x's by each other, and it's homogeneous because of the 0. So I'm going to guess r e to the nt. If it works, I'm done. If it doesn't work, I go back and try something else. Now I'm going to plug this into my equation. I'm going to have to take 3 derivatives. So r1 is e to the nt n. X double prime is r e to the nt n squared. X triple prime is r e to the nt n cubed. Plugging that into my original differential equation, x triple prime is r e to the nt n cubed plus 2 times x double prime is 2 r e to the nt n squared minus x prime r e to the nt n minus 2 times x is 0. Every term has an r e to the nt. If that doesn't happen, you did something wrong. That should always happen. So I can factor that out, leaving me with an n cubed for the first term, plus 2n squared for the second term, minus n for the third term, and the last term is minus 2. I don't want r to be 0. If r is 0, my x is 0 and I don't have a solution. That means that the cubic term, n cubed plus 2n squared minus n minus 2 is 0. So now I don't have the quadratic equation. So I'm going to basically just make a guess here. And if I make a guess and it works, that's good. Or I could graph it, which is actually what I did. I graphed it and I saw n equals 1. If you don't see that, just try n equals 1. Let's see. So 1 cubed plus 2 times 1 squared minus 1 minus 2 gives me 1 plus 2 minus 1 minus 2 is 0, so that is a root. Why is that a big deal? That's a big deal because that means I can write n cubed plus 2n squared minus n minus 2 is n minus 1 times some quadratic. I don't know what that quadratic is, but I can now use division, polynomial division, to figure it out. I'm going to use just regular polynomial division. If you are used to using synthetic division, that's fine. It's basically the same thing, just different notation. So whichever works for you is fine. So what do I multiply n by to get n cubed is n squared, because n squared times n is n cubed. So n squared times n is n squared minus 1 times n squared. N cubed minus n cubed is 0. 2n squared minus a minus 2n squared is plus 3n squared. And I'm just going to bring down the rest. What do I multiply n by to get 3n squared is 3n, because 3n times n is 3n squared. 3n times minus 1 is minus 3n. So 3n squared minus 3n squared is 0. Minus n minus 3n, minus n minus a minus 3n is plus 2n. And so finally, to multiply n by 2 will give me the 2n. So 2 times n is 2n, 2 times minus 1. When I subtract those, I get 0. If you do not get 0 there, you did something really wrong, and you need to go back and check your work. But what does this say? This says that n cubed plus 2n squared minus n minus 2 is equal to n minus 1 times this thing on top. Now I have a quadratic, and I can either factor to use the quadratic equation, but I can see offhand that this is n plus 1 times n plus 2. So that's a lot. So notice here you have to be very organized and neat, and you're keeping track of a lot of stuff. My original differential equation was x triple prime plus 2x double prime minus x prime minus 2x equals 0. I assumed a general form, and I got, from my differential equation, I got a polynomial n cubed plus 2n squared minus n minus 2 is 0. And I was able to factor it to n minus 1 times the quantity n plus 1 times the quantity n plus 2 is 0. So that means n could be 1, could be minus 1, or it could be minus 2. So that means my x of t is going to be r1 e to the 1 times t plus r2 e to the minus 1 times t plus r3 e to the minus 2 times t. Okay. From this, you should be able to tell me, how does this thing behave? E to the minus 2t decays. It decays faster than e to the minus 2t, or e to the minus t. So just looking at those two terms, this is the dominant term. But I also have to consider this third term, because I'm adding all of these things together. That thing grows like e to the t. So if I'm adding this to this to this thing goes to 0 very fast. This thing goes to 0 more slowly, but this thing grows. So after a short amount of time, you're basically adding this to 0. This is the thing that grows or matters the most. So the dominant term is e to the t, and the thing grows exponentially like e to the t. So given this differential equation, you should be able to get the general solution, and you should be able to tell me it's going to grow like e to the t. Okay, last example. And I'm going to basically just state the solution rather than go through and do all that. Well, I may change my mind. Let's see. Suppose I'm given this differential equation. So x triple prime plus 11x double prime plus 38x prime plus 40x equals 0. It's third order because of that. It's linear because x's are by themselves, and it's constant coefficient because in front of each term is a constant, and it's homogeneous. And because of all of those things, I should say it's homogeneous because that's at 0, I'm going to make a guess. And if this guess works, then I'm done. If it doesn't work, I'm not done. Okay, so let's see. I'm going to plug this into my equation, so I need to take 3 derivatives. First derivative is re to the nt times n. Second derivative is re to the nt times n squared. And the third derivative is re to the nt times n cubed. If I plug this back into my original equation, x triple prime is re to the nt n cubed plus 11x double prime. X double prime is e to the rnt n squared. X prime is 38 re to the nt times n plus 40x. X is re to the nt is 0. Every term has re to the nt. So I can factor that out. If you cannot factor that out, you did something wrong. So that's a quick way to check your work. I'm left with an n cubed for this term. Here I'm left with an 11n squared. Here I'm left with a 38n. Here I'm left with just 40. And I don't want that to be 0 because that's my solution. If that were 0, that would be bad. I got to figure out something to plug into there. Notice if I plug in 1, I'm going to get 1 plus 11 plus 38 plus 40. I'm just adding numbers up. So any positive number is not going to work. So that's out. If I try minus 1, I'm going to have minus 1 plus 11 is 10. Minus 38 is going to be what? Minus 28 plus 40. That's not 0. Okay, I'm going to try minus 2 and hope it works. Or again, you could just go into Desmos, graph it, and look at it. But on a quiz or test, you can't do that. So you just hope that I gave you something nice. If n equals minus 2, we have minus 2 cubed plus 11 times a minus 2 squared plus 38 times minus 2 plus 40. So minus 2 cubed is 8. Minus 2 squared is 4 times 11 is 44. Minus 2 times 38 is going to be what? Minus 76 plus 40. So let's see. So minus 8 plus 44 is going to be what? Minus 36. Minus 76 plus 40 is, oops, sorry, that's going to be plus 36. Minus 76 plus 40 is minus 36 is 0. So n minus 2 works. That means n minus a minus 2 is a factor of my original cubic. I just need to figure out what that is. But that means that I can factor out n plus 2 from this cubic. I'm going to go ahead and do this because I love algebra. So I've got to figure out how do I divide this out. Again, if you prefer to use synthetic division, that's fine. This is more fun, so I'm going to do this. So how many times does n plus 2 go into n cubed plus 11n squared plus 38n plus 40? So what do I multiply n by to get n cubed? That's n squared. So n squared times n is n cubed. Then plus 2 times n squared. n cubed minus n cubed is 0. 11n squared minus 2n squared is 9n squared. Let's bring everything else down. What do I multiply n by to get 9n squared? This can be 9n. So 9n times n is 9n squared, plus 9n times 2 is plus 18n. 9n squared minus 9n squared is 0. 38n minus 18n is 20n. Bring the 40 down. Now multiply n by 20 to get 20n. So 20 times n is 20n. 20 plus 2 is 40. And when I subtract that, I get 0 plus 0. Again, if you do not get 0 there, something terrible happened. This says that n times 2 plus n squared plus 9n plus 20 is equal to my original cubic, which is what's inside here, is n cubed plus 11n squared plus 38n plus 40. And notice here I can factor out this. That's going to be n plus 4 times n plus 5. If you do not see this, just use the quadratic formula and you can get it. So that means either n is minus 2, n is minus 4, or n is minus 5. So my solution to my original differential equation is x of t is r1 e to the minus 2t plus r2 e to the minus 4t plus r3 e to the minus 5t. Notice minus 2 is the largest of those numbers, which means that is going to be the dominant term. So this decays to 0 really fast. This decays to 0 the next fastest. This decays to 0, but not nearly as fast as these other two. So after a short amount of time, this is really close to 0. This is close to 0, much closer than e to the minus 2t. And so you're basically adding this up to zeros. So the dominant term is e to the minus 2, which implies the solution is going to decay like e to the minus 2t.